Hello viewers, we are now taking you through the story for A-level pure mathematics. And this video I'm going to go through the topic of differential equations. So this video is suitable for students in both senior 5 and senior 6 offering principal mathematics as part of their combination. So far the progress on this platform is as follows. Where you see the ticks, it implies that the topics were covered, and the ones without ticks are the ones which have not yet been covered. So math paper 1 is divided into 5 parts. So the first part is algebra, where 2 questions come in section A and 2 in section B. The second part is trigonometry, where 1 question comes in section A and 1 in section B. The third part is geometry, where 1 question comes in section A and 1 in section B. Fourth part is vectors, where 1 question comes in section A, 1 in section B. And the last part is calculus, where 3 questions come in section A and 3 in section B. So far we have, where you see the ticks on calculus it has been covered. Now we are going to cover differential equations. So a differential equation is an equation containing differential coefficients or derivatives, and there are some terms which you need to know under these topics. So one is linear differential equation. So a differential equation is linear in y if its order decreases gradually by 1. For example, here this one is of degree 2 because you see here 2, this is the second derivative, first derivative, and y, so that means that it is linear. Then another term is nonlinear differential equation. So a differential equation is said to be nonlinear if its differential coefficients are raised to a power greater than 1. For example, if this first derivative is raised to the power 2 or more, it becomes nonlinear. Also, if the second derivative is raised to the power 2 or more, it becomes nonlinear. The next is what we call differential coefficients. So a differential equation is said to have constant coefficients if all the coefficients of the derivatives are constant. If one of the coefficients is variable, then the differential equation is said to have variable coefficients. So in other words, differential coefficients are these ones on the first derivative and also on y and also on the second derivative. So here the second derivative has 1 as its differential coefficient, first derivative has 4x as the differential coefficient, and y has 5x squared as the differential coefficient. So that is what we call differential coefficient. Then another term is solution of a differential equation. So that the solution of a differential equation containing dy dx involves finding the equation connecting x and y without containing the derivatives. So this is very vital because it will take a large part in this video. I think we realize that we are only interested in dy dx. So the second derivative is of no interest when you're solving differential equations at this level. So the solution is obtained by or through integration. So some students, when they hear the word differential, they think that it's under differentiation, but this is not the case. We need integration to solve differential equations. Why? Because we already know that the reverse of differentiation is integration. So if you are given dy dx and you're told to get to y, it implies that you have to integrate. Now in the solution, there are 2 parts of the solution. One is the general solution, and this general solution, the constant remains. So a general solution of a differential equation is a solution containing an arbitrary constant. In other words, the constant after integration remains. Remember, when you're integrating an indefinite integral, the constant of integration must be seen. So in this case, if after integration the constant remains in your solution, we call it a general solution. But sometimes they can give you some initial conditions, and when they give you the initial conditions and you use those initial conditions to get the value of the arbitrary constant or the constant integration, it implies that now it is no longer a general solution but a particular solution. So we shall see both these solutions in the worked examples. Then we also have what we call the order and degree of a differential equation. So the order of a differential equation is determined by the highest derivative present in the differential equation. Then, for example, here the order of this one is 2 because the highest derivative is the second derivative. That is why we call it second order. Also here the highest derivative is the second derivative, meaning it will be second order. Also here the highest derivative is the first derivative, meaning it will be first order. So that is how they get the order of a differential equation. What about the degree of a differential equation? So the degree is determined by the power of the highest derivative present in a differential equation. So if, for example, in this case the highest derivative is this second derivative and the degree is 2 and the power on it is 2, meaning that the degree will be 2. Here the highest is the second derivative and the power is 1, meaning that the degree will be 1. Here the highest is first derivative and the power on it is 2, meaning that the degree will be 2. So those are the terms we need to know under differential equations. So we shall go to the first part, which involves forming differential equations. So sometimes they can give you a differential equation and they tell you to solve it, or they can give you an equation and tell you to form a differential equation. So in this first part we are going to deal with forming a differential equation. In other words, they give you an equation and you have to form a differential equation. So question 1 came from UNEB 2011 paper 1 question 8 and says, part A, form a differential equation by eliminating the constants a and b from this equation. Then part B, state the order of the differential equation formed in A above. So first of all we have that x is equal to this. So we shall differentiate. When I differentiate the first time, differentiate this, I think you remember how to differentiate trig functions. When I differentiate this, I come up with negative a sine t, and when I differentiate this, I come up with b cos t. That is called the first derivative. Then the second derivative, it means that I differentiate this to come up with negative a cos t, differentiate this, I'll come up with negative b sine t. So when I rearrange this, I realize that negative is common. So when I pull out the negative, I'll come up with, in brackets, it will be a cos t plus b sine t. And the good thing, we know that a cos t plus b sine t is equal to x. Therefore, we shall come here and say that the second derivative is equal to this negative here and this one, which becomes x. So put everything on one side, you come up with that, and this will be our differential equation which they wanted. Then part B, they wanted you to state the order. So the order, in this case, you shall say that the order is 2 because the highest derivative is the second derivative. So that was question 1. Now we shall go to question 2, which came from UNEB 1988 paper 1 question 13a, and says, given that y is equal to this exponent 2x sine 3x, prove that this is equal to 0. So we are given this. The first thing to do is to differentiate. Now before we differentiate, we must realize that this is a product, so we shall use the product formula. Product formula says keep this constant and differentiate this. So when I differentiate that, I'll come up with 3 cos 3x. Then plus keep this constant, which is here, and differentiate this. So when I differentiate this, I'll come up with 2x minus 2x. So this e means an exponent, exponential. So I can try to simplify to come up with that. And the good thing, I know that e 2x sine 3x is the same as y. Therefore, this one will be replaced by y. That will be equation 1. The next we shall differentiate the second time. So differentiating the second time, this one is also a product. So what we are going to do, keep this constant which is there, then differentiate this to come up with this, plus keep this constant which is here, then differentiate this to come up with this. Then this one, differentiating this gives you 2 dy dx. So simplifying will give us that. So this is that, this is this, and this is that. So next we shall also realize that this one is also found here. So you come and replace it with y. So that is why you see this y there. Now from equation 1, we know that this is equal to this. Therefore, we are going to substitute this one here to come up with that. When I open brackets and try to rearrange, I'll be able to come up with the required differential equation. So now we shall go to question 3, which is that given that y is equal to this, show that this is equal to 0. So first of all, we know y is equal to that. Therefore, we shall come and differentiate. The first time to get this gives you this, and this gives you this with a negative. Then differentiate the second time, this gives you that, and this gives you this. But the good thing, we know that y is equal to this. Therefore, what you're going to do, we shall come and first split this one into 2. This 9, this will be split into 3, that, and so the 6 is there. Then this 4 will be split the same as negative this and also positive that. Now, why are we doing that? It is because when you look at this first derivative, I'll first extract it out from this equation, from the second derivative. So when I remove 3 here, I remain with 6. That's why I put 6 here. And when I remove this negative 2 here, I remain with positive 6. That is why you see positive 6 there. So negative 2 plus 6 gives you positive 4, which is here. So next is to substitute. So where there is this, I'm going to put there dy dx. So the whole of this, I'm going to put there dy dx. Then also this one, if I factorize out 6, I'll be able to remain with this. So where there is that, I'll put there y. That is where the 6y is coming from. Rearrange and you'll be able to get the required differential equation. So that is how to form differential equation. Now we shall go to the other part, which deals with first order linear differential equation. Now, solving differential equations, in solving we only deal with first order. Second order and higher orders, we don't need them at this level. That is why we only want first order. So first order means that it is only the first derivative. Therefore, these are gradually in the form dy dx plus py equal to q, where p and q are functions of x. Now, these p and q are not constants. They are functions in themselves. So these first order differential equations are grouped into 2 major categories. The first one is those with separable variables, and they are called separable differential equations. Then the other part is non-separable variables, and they are called non-separable differential equations. So both these parts will be looked at in this video. Now let's start with the first part, which is separable differential equations. So these ones are generally in the form dy dx equal to the function of x multiplied by the function of y. Note that this is a multiplication sign. If it is plus or minus, then it is no longer separable. Now why do they call them separable? It is because you can separate, you can put y on one side and also x on one side. For example, if I bring this one this side, I can take this one this side so that the left hand side has only y and the right hand side has only x. That is what it means by separable. It means that you can separate them. So solving separable differential equations requires the following steps. So to solve these equations, first separate the variables. Put x on one side and also y on one side, but remember this dy and this dx must be in the numerator, must be part of the numerator, and then apply direct integration in order to obtain the equation connecting x and y without containing the derivative. So after separating variables, you put integrals on both sides and then proceed with the methods of integration. What you get is what will be the answer. So basically that is how they solve separable differential equations, and we shall go through a number of worked examples for you to grasp this concept of solving separable differential equations. Like I've already told you, math is not read but practice. So if you just read this, you may not easily understand what it means, but as you practice, you'll be able to understand what it means. So let's go through a number of worked examples from the UNEB Question Bank. Let's start with the one for last year. Question 1 came from UNEB 2020, paper 1, question 16, and says, part A, solve the differential equation this, given that s is equal to that and s is equal to that when t is equal to 0. And part B, determine the value of Roman 1 t when s is equal to 16 and Roman 2 s when t is equal to 2.4. Give your answer to two significant figures. So we are given that ds dt is equal to 2 exponential 2t over root s. So this is separable. So what you are going to do, we are going to put s on one side. Remember we said the ds and the dt must be in the numerator. So this one means that ds is already in the numerator, meaning that s will be on the left hand side and t will be on the right hand side. So what you are going to do, we are going to put this s this side to come up with root s ds, and put this t this side to come up with 2 exponential 2t dt. That is the first step, separate the variables. And then the second step is to put integrals on both sides. So put integral here and here, as you can see on this step. The next is to use the knowledge of integration, which already covered under further integration and also integration 1. But this one is under integration 1 and this one is under further integration. So both videos are available on this platform. So now integrating this gives you that, and integrating this gives you that, plus the constant of integration. But you are given that s is equal to 9 when t is equal to 0. So what does that mean? It means that we shall come here and substitute for t and for s. Where there is s, we shall put there that. So 9 cubed gives you this, and where there is t, we shall put there 0. That's why you see 0 there. So this one gives you 1, and this one gives you 18. What does that mean? It means that c is equal to 17. Therefore, you shall come and bring this c here to come up with the equation they want. So in that case, we have solved the differential equation because there's nothing like derivative in this equation. Now when you go to part B, Roman 1 side, determine the value of t when s is equal to 16. So when s is equal to 16, you shall come and put 16 here, then make t the subject. So when you make t the subject, you shall be able to come up with the value of t. Now at this point, there is an exponential, so what we shall do, we shall put ln on both sides. I believe you know what ln means by at this point, because we already covered them under further integration. So put ln on both sides. This will give you ln that, and this side will give you ln this. But ln and exponent is cancelled, so this side shall remain with only 2t. That's why you see here 2t equal to ln this. So now next is to make t the subject, and when I make t the subject, t will be equal to a half ln 77/3, which approximates to 1.6 to 2 significant figures. Remember, they told you to give your answer to 2 significant figures. So now we shall go to Roman 2. So Roman 2, they want the value of s when t is equal to 2.4. So we shall come here and say that when t is equal to 2.4, then the formula equation becomes that. So where there is 2, we shall put there 2.4. Then you shall remember that this one, square root of s cubed, is the same as s to power 2/3. I think remember that under indices from O-level. Then this one has gone this side to become 3/2. Now next is to make s the subject. So when this power goes this side, it becomes the reciprocal. That's why you see here 2/3 instead of 3/2. The next is to use the calculator. We'll come up with this, which approximates to 40 to 2 significant figures. So now we shall go to question 2, which came from UNEB 2017, paper 1, question 16, and says, solve the differential equation this, given that y is equal to 1 when x is equal to 1, and hence find the values of y, find the value of y when x is equal to 4. So first of all, this is separable, so the first step is to separate the variables, meaning we shall put y on the left hand side and x on the right hand side. Why? Because this dx and this dy must be numerators. So for this dx to be a numerator, it has to go this side. Therefore, x variables must be put on the right hand side. So next is to put integrals on both sides. And after that, we shall integrate using the knowledge of integration. So integrating this gives you that. And this one will need integration by parts. So what we shall do, we shall let u to be equal to this, and du, therefore du dx gives you, when I differentiate this, gives me 1/x. Now this other part will become our dv dx, therefore dv dx will be x to the power half. When I integrate it, I'll come up with v equal to 2/3 x to the power 3/2. Then I'll quote the formula for integration by parts, then I'll substitute. That means that this integral is this one, which is here. So, and to be equal to uv, u is this, and v is this. So when I multiply the two, I'll come up with this part. Then minus integral of v, so v is this, and u dx is this. So when I multiply these two, I'll come up with this. So now my aim is to get that integral. So when you simplify that part which is to be integrated, we shall come up with 2/3 x to the power half. And when I integrate, I'll come up with that. Therefore, I'll go back to my equation 1 and be able to substitute. When I substitute, I'll come up with this. But remember, we are given that y is equal to 1 when x is equal to 1. So this initial condition will help us to get the value of c. So when I substitute for y and x, I'll come up with that. That implies that x will be equal to 22/9. Therefore, this c will be equal to 22/9, and that c will come and be replaced with this to get the particular solution. So this one is what we call the general solution, and when you substitute the constant of integration, you shall come up with the particular solution. So each time they give you initial conditions, it implies that they want the particular solution, and when they don't, it implies that they want the general solution. So when I try to multiply through by the LCM, which is 9, I'll come up with that. Now it is okay to stop at this point, or you can proceed further to get this point. You'll still get all the marks. So in the question, they told you to find the value of y when x is equal to 4. So you come and say that when x is equal to 4, what happens? You come and replace x with 4 and make y the subject. So when I make y the subject, y will be equal to 7.2726. So that was question 2. Now I shall go to question 3. Question 3, which came from UNEB 2016, paper 1, question 4, and says that solve the equation this, given that y is equal to 1 when x is equal to 0. So first of all, we shall separate the variables and put integrals on both sides. Then we integrate. So integrating this gives you tan y, and integrating this gives you x, plus the constant of integration. But we already know that y is equal to 1 when x is equal to 0, so we shall substitute and be able to get the value of c. Remember, calculator should be in radians, that's why here we are putting there pi over 4. If you put 45 degrees, that will not be okay. So next we shall substitute this c here and be able to come with the equation which they want. Therefore, y, you can either stop here or you can say that y is equal to that. So now we shall go to question 4, which came from UNEB 2016, paper 1, question 13b, and says the gradient of the tangent at any point on a curve is this. The curve passes through the point to 4. Find the equation of the curve. So gradient is dy dx. So dy dx will be equal to this. The next is to separate the variables and put integrals on both sides. After that, we shall integrate, use the knowledge of integration. So this gives you that, and this gives you this, plus the constant of integration. So at this point, it implies that x is equal to 2 when y is equal to 4. So you come and substitute for x and y to be able to get the value of c. After getting the value of c, we shall substitute it here to be able to get the particular solution. So I can choose to simplify further. So this and this gives you this. And now that here the question is 1 here, and also here the question is 1, you can easily remove this ln and this ln to come up with that. Therefore, x squared y is equal to 16. Now we shall go to question 5, which came from UNEB 2015, paper 1, question 8, and say that solve this given that y is equal to this when x is equal to 0. So the first step is to separate the variables. So you should realize that this one is the same as this. Then when you separate the variables and put integrals on both sides, you'll come up with this line. The next is to integrate. So this one gives you this and this gives you that, plus the constant of integration. But you already know that y is equal to 2 when x is equal to 0, so you shall substitute for y and for x and be able to get the constant of integration. Then after that, we shall substitute that constant in this equation to come up with the particular solution. So you can choose to rearrange, or you can choose to rearrange and calculate the terms to come up with that. So now we shall go to question 6, which came from UNEB 2013, paper 1, question 8, and say that solve this given that y is equal to 1 when x is equal to 0. So like I said, the first thing to do is to separate the variables. So look for a way of separating the variables. You shall first put this on this side to come up with this line. Then after that, you should realize that the y is on the left hand side, meaning that the left hand side will have y variables and right hand side will have x variables. So when you do that, it means that this one must come this side to come up to become x over 1 minus x squared dx, and this y will come this side to become 1 over y squared dy. Put integrals on both sides to come up with this line, then integrate. So integrating this gives you this, and this gives you that. So, but I already know that y is equal to 1 when x is equal to 0, so I'll come and substitute for y and for x to come up with the value of c. After that, I shall substitute here to come up with the particular solution. Therefore, y is equal to 2 over 2 plus ln 1 minus x squared. So now I shall go to question 7, which came from UNEB 2011, paper 1, question 16a. And it says, solve the differential equation this, given that y is equal to 1 when x is equal to 0. So this is what is given. Next is to collect like terms. So take this one this side and take this one this side to come up with this, and then put integrals on both sides. So now at this step, we are thinking to remember the method of integrating powers of sine, even powers of sine. We have to first use double angle identity. So those methods are available in the video of integration of trig functions. This one is okay because you use the knowledge of integration 1. So this one will give you this, but this one we have to first use double angle identity to come up with this. Then after that we can now easily integrate. So integrating 1 gives you x, and integrating this gives you a half sine 2x. Then we can open brackets to come up with that. But we are given that y is equal to 1 when x is equal to 0. Therefore, come and substitute for y and x to be able to get the value of c. After getting the value of c, we shall substitute it here to come up with the differential equation which they want. Now we shall go to question 8, which came from UNEB 2009, paper 1, question 8, and says, solve the differential equation this, given that y is equal to 1 when x is equal to e. Now that e means an exponential. So the first thing to do is to collect like terms, put y on one side and x on one side. So when we do that, we shall come up with this, then put integrals on both sides to come up with this. So now here, this one is easily integrated by splitting the numerator. So when I split the numerator, I'll come up with this part. Then I can now easily integrate. So this one gives you ln that, and this one gives you that, this one gives you that. But y is equal to 1 when x is equal to e. Therefore, I'll come and substitute to be able to get the value of c. Then I'll come and substitute for c here to get the particular solution. And that will be the answer. So now we shall go to question 9, which came from UNEB 2005, paper 1, question 16a, and say that solve the differential equation this. So the first thing to do is to collect like terms and put integrals on both sides. Then this one, 1 over sec is the same as cos, therefore 1 over sec squared will become cos squared to give you this. For this side, we have to use integration by parts. And this side, we have to use the double angle identity because it is an even power. So double angle identity for this gives you that. Then for this part of integration by parts, we shall need a table. So we shall tabulate 3 columns, one having sine, another one having differentiation. Differentiation, we shall put there x. So when I differentiate x, I'll come up with 1, and when I differentiate 1, I'll come up with 0. So when I stop reach 0, that's where I will stop. Then the column for integration, I'll put there this, which is sine x. Integrate sine x, I'll come up with negative cos x. Integrate negative cos x, I'll come up with negative sine x. Then from there, I can now easily integrate. So for this side, integrating 1 gives you y, integrating this gives you that. Then for the right hand side, what we do shall get this times this times this to give you this. Then this times this times this to give you that. So that is how they integrate by parts. then simplify to come up with that. So now we shall go to question 10, which came from UNEB 2003, paper 1, question 16a, and says, solve the differential equation this, given that r0 is equal to 3. So the first thing to do is to collect like terms and put integrals on both sides. Then integrate. So when I integrate this, I'll come up with r. Integrate this, I'll come up with this. This, I'll come up with that. Plus the constant of integration. But we are given that r0 is equal to 3, meaning that r is equal to 3 when t is equal to 0. Then we'll come and substitute for r and t to be able to get the value of c, and then substitute that c here to get the particular solution which they wanted. So now shall go to question 11. Question 11 came from UNEB 2001, paper 1, question 8, and says, solve the differential equation this, given that x is equal to 4 when y is equal to 6, and hence determine the value of x when y is equal to 10. So the procedure will always be the same. First is to rearrange and separate the variables, and then put integrals on both sides. So this y will go this side to become 1 over y dy, and this dx will come this side to become 1 over 2x plus 1 dx. Then you put integrals on both sides. So next is to integrate. When I integrate this, I'll come up with this, and this gives me that, plus the constant of integration. But the good thing, I know the initial condition that x is equal to 4 when y is equal to 6. Therefore, I'll come and use those ones to come up with the value of c. So I'll come up with c as ln of 2. Therefore, I'll substitute this c in this general solution to come up with a particular solution. So I can easily simplify, because this half can go this side to become 2x plus 1 raised to the power half. Now that power half is the same as the square root, and this one going this side, it becomes ln y minus ln 2 to become ln y over 2. Therefore I can cancel these ones, because there is the quotient here is 1 and also here is 1. So when I cancel the lns, I'll come up with y over 2 equal to square root of this. Then square both sides and take this to this side. You'll come up with y squared equal to 4 in brackets 2x plus 1. So someday we'll cover something called parabola. So this is an equation of a parabola. Now they wanted us to get the value of x when y is equal to 10. So we shall come and say that when y is 10, come and substitute for y and make x the subject. So when I do that, I'll come up with x being equal to 12. So now we shall go to question 12. Question 12 came from UNEB 1993, paper 2, question 9b, and says, solve the differential equation this, given these initial conditions. So the first thing to do is to rearrange and separate the variables. So when I separate, I'll come up with negative 1 over y squared plus 1 dy, and this side it will be 1 over x squared plus 1 dx. Then I have to put integrals on both sides. After that, I will have to integrate. So when I integrate, I'll come up with negative arctan y this side, and here it will be arctan x plus the constant of integration. So this is a standard integral, and it gives you arctan y, and this also standard integral, it gives you arctan x. But we are given that x is equal to 0 when y is 10, when y is 1. Therefore, we shall come and substitute for y and x in this general solution to come up with the value of c. I think remember that as long as there's trigonometry, the calculator should be in radians. So this angle must be written in radians. If you write 45 degrees, that will not be okay. It will not be okay. So c is equal to negative pi over 4. Then we'll come and put this c there to come up with a particular solution. And basically that is what they wanted. So now we shall go to question 13, which came from UNEB 1992, paper 1, question 9b, and says, solve the equation this, given y is equal to 1 when x is equal to 0. So still the same procedure, I'm going to rearrange and separate the variables. Then when I separate variables, I'll come up with 1 over y plus 1 dy, and here it will be x over x squared plus 1 dx. Then put integrals on both sides. All that you will integrate. So this gives me ln y plus 1, and this gives me a half ln x squared plus 1, plus the constant of integration. But I already know that y is equal to 1 when x is equal to 0, so I'll come and substitute for y and x to be able to come up with the value of c. So the value of c will be, remember, ln 1 is equal to 0, that's why you see 0 there. So c will be equal to ln 2. Therefore, I'll come and substitute this c here to come up with a particular solution. So when I collect like terms, so this will come this side to become ln y plus 1 over 2. Then this half will go up here to become ln square root of x squared plus 1. Then when I cancel these lns, I'll come up with this equal to that. Therefore, y plus 1 squared is equal to 4 in brackets x squared plus 1. So now we shall go to question 14. Question 14 came from UNEB 1989, paper 2, question 9, Roman 1, and says, solve the equation this given that y is equal to 0 when x is equal to 0, expressing y as a function of x. So we are given dy dx as that, so the first thing to do is to separate variables and put integrals on both sides. All that we shall integrate, so this gives you this and this gives you that, plus the constant of integration. But we are given the initial conditions that y is equal to 0 when x is equal to 0. Therefore, we shall come and substitute in order to get the value of c. So when I substitute, I'll be able to come up with c as ln 3. Then when I substitute this c in this general solution, I'll be able to come up with a particular solution. But in the question, they told us to express y as a function of x. In other words, we have to look for ways of making y the subject. Therefore, what I'm going to do, I'll first bring this one this side to come up with ln y plus 2y plus 3 over 3 equal to x. Then put exponential on both sides to come up with, so this ln this it cancels, we remain with only this. That's why you see here this without any ln or exponential. But here when you put e here, it will become ex. So whatever you do on the one side, you have to do it on the other side. So what you have done to move from this step to this step is to put exponential on both sides. The next is to cross multiply, take this one this side to come up with that. The next is to make y the subject, so y will be equal to 3 over 2 in brackets ex minus 1. So that was separable differential equations. Now we shall go to the second part, which is non-separable differential equations. So these are differential equations which cannot be solved by separating variables. So in other words, there is no way you can separate variables as we have been doing. Therefore, there are 3 forms of such non-separable differential equations. One is homogeneous, another one is exact, another one is inexact differential equation. So let's start with this one, which is homogeneous. So a homogeneous differential equation is one in which all the terms are of the same degree. That is, all the terms are of the same dimensions. E.g., for example, if I look at this, now dimensions means where there is x, you will put there capital L, where there is y, you put there capital L. dy dx will put 1 because change in y is L, change in x is L, so L over L is 1. Then here you will become L squared, here to become L squared, just as you can see it here. So this is for x, this is for y, this is for dy dx, this is for L squared, this is for y squared. Now if you look at this one cancels, you remain with L squared, which is this, and this is L squared, this is L squared. Now when all are the same, it implies that it is homogeneous. If they are not, then it is no longer homogeneous. It is either exact or inexact. So the reason why we first test to see whether it's homogeneous is to use a method that can easily give us the solution, because homogeneous differential equations are solved in a different way from that which is exact or inexact. So for this case here, this L, this is L over L, this is L, this is L. So in the end we come up with this, meaning that it is homogeneous because they all have the same dimension. So that is how you can find out whether the differential equation is homogeneous or not. But remember, the first step to look for is whether it is separable. If it is not, check whether it is homogeneous. If it is not, then there is only one option for solving such a differential equation, as we shall see towards the end of the video. So let's see how homogeneous differential equations are solved. So these are solved by using an appropriate substitution of y equal to ux, where u is the function of x. Now this u is not a constant, it is a function of x. Therefore, when you want to differentiate y, you have to remember product rule. So product rule says that y dx will be equal to, keep this one constant, which is that differentiate x, you come up with 1. That is why you only see u here. Then keep this one constant, which is that then differentiate u to come up with du dx. So that is our dy dx. So we have y and we also have dy dx. What next after that? So this substitution helps to transform the homogeneous non-separable differential equation into a separable differential equation. So these two are substituted in the given differential equation, and as you simplify, you realize that the outcome is a separable differential equation. If it is still not separable, it implies that there is a mistake somewhere in the solution. So at this stage, the method used to solve separable differential equations can be adopted. So let's look at some of the worked examples. So question 1 says, using the substitution y equal to ux, solve the differential equation this. So first of all, you are going to differentiate this y here to come up with this, as we already seen. Then next is to substitute in the given differential equation. So this is what was given, so I'm going to substitute for y and for dy dx. When I do that, I'll come up with this. So here, if you are keen, you realize that this x squared is common throughout and can cancel out. But even if it doesn't cancel out at this other step, you can first expand as I've done here. Then at the end, it will cancel out by itself. So out expanding, you can easily see that it cancels out. So this will cancel with, and here to the remaining one x, because it is cubed, then this one will also cancel. So in the end, you come up with u plus x du dx equal to 1 plus u squared. So I think this is separable. So the first thing to do is to rearrange, because this u and this u cancels, and you remain with x du dx equal to 1 plus u squared. Then next is to separate the variables and put integrals on both sides, as we have been doing under separable differential equations. The next is to integrate. This gives you arctan u and this gives you ln x plus the constant of integration. So they didn't give us the initial conditions, meaning that they only wanted the general solution. So I can choose to substitute for u, because u, remember, it is here, but they want in terms of y and x. Therefore, u will be, where there is u, you'll come up with y over x. So now we shall go to question 2, which says that solve this differential equation. So this is already homogeneous because this is L squared, L squared, L squared. Therefore, still the first thing to do is to let y be equal to this and then get its derivative. Then substitute in the given differential equation. So this is the given differential equation. I'll substitute for y and dy dx to come up with that. Then open brackets to come up with that. Then from there you'll realize that x squared is common, so it will cancel here to remain x, but here it cancels, here it cancels. Then also after that you realize that this u also cancels, so you remain with x du dx equal to u squared. Then now this is a separable differential equation. The first thing to do is to separate variables and put integrals on both sides. After that, I'll start integrating. So this gives you negative 1 over u, and this gives you ln x plus the constant of integration. So I can choose to write this c to become ln, in terms of ln, to become ln c, to become ln k, so that I can write it as ln kx. Then when I do that, it implies that, remember, u was y over x, therefore 1 over u is x over y, as you can see it here. Therefore, e exponential of negative x over y is equal to kx. So now we shall go to question 3, which says that using the substitution this, where u is a function of x, solve the differential equation this, given that y3 is equal to 1.5. So the first thing to do is to get its derivative, the derivative of y, and after that you will substitute in the given differential equation. Then you're going to simplify until you get a separable differential equation. So this differential equation is separable, so I'll separate the variables and put integrals on both sides. Now when I integrate this, I'll come up with this, and this I'll come up with this plus the constant of integration. So I can either use it in this format, or you can say that let this constant of integration be equal to ln kx. Therefore we'll come up with this let this c be equal to ln k. Therefore we'll come up with this side, it will be now become ln kx, because it will be ln x plus ln k, which will be ln kx. So now I can cancel this ln to come up with u plus 1 equal to kx. U will be equal to kx minus 1. But I already know that u is equal to y over x, so I'll come and substitute for u to come up with that, then cross multiply to come up with this as the value of y, as the expression of y. So I was given some initial conditions. y3 is equal to 1.5. That means that y is equal to 1.5 when x is equal to 3. Therefore, I come and substitute for y and for x to be able to come up with a value of k. And the value of k will be a half. Therefore, y is equal to a half x squared minus x. So that was homogeneous differential equation. So now we shall go to the last part, which is exact and inexact differential equations. Now these two differential equations are different, but the good thing is that the same one method can be used to solve both differential equations. So that means that there's no need to find out whether it is exact or inexact, as long as the differential equation is not separable and it is not homogeneous. Then the only option is that it is exact or inexact, and both exact and inexact differential equations, the same method applies to both of them. So if a non-separable differential equation is not homogeneous, then it is either exact or inexact. And in other words, it is in the form dy dx plus py equal to q, where p and q are functions of x. So a differential equation in this form is not homogeneous, because here the dimension is 1, here the dimension is L squared, and here it is L. So since they are different, it is not homogeneous, and it is also non-separable because you cannot separate the variables. Therefore, the only option is that it is either exact or inexact. Now, after realizing that, there is no need to go further to find out whether it is exact or inexact. Why? Because the same method is used to solve both exact and inexact differential equations. So as we go through the worked examples, we will be able to realize whether the differential equation is exact or it is not. So the following are the steps which are taken to solve such differential equations. 1. So such equations are solved with the help of what we call integrating factor. So consider a general form of an exact or inexact differential equation. So this is the general form of a differential equation which is either exact or inexact. where p and q are functions of x. So the steps taken are these ones. So the step 1 is calculate the integrating factor r. So this capital R denotes the integrating factor, and this integrating factor is got by exponential of the integral of p dx. Now what is p? P will be the coefficient of y. Now if here there is y, then it means that you look for the coefficient of y, and that will be the value of p, on condition that here there is no coefficient of dy dx. In other words, or you can say that the coefficient of dy dx is positive 1. If here there is a certain value, say 2, you have to first divide it throughout by 2 so that here the coefficient remains positive 1. That is how you can get the value of p which you are going to integrate, the function p which you are going to integrate. So that is step 1, you have to first get the integrating factor. Then step 2, multiply the integrating factor r throughout the given differential equation. So this was the differential equation, so I'll multiply this to come up with this. Here you put also here r, here you also put r. Now at this step you can easily find out whether the differential equation was exact or inexact. How? If after multiplying throughout by this r you get the same differential equation as before, it implies that the differential equation was exact. If not, it was inexact. But like I told you, there's no need to bother to distinguish between these two differential equations, because the same method is used to solve both equations. So that is step 2, multiply throughout by the integrating factor. Then step 3 is more of stating. So after step 2, the resulting equation will be an exact differential equation. Hence, the derivative of y times r is equal to qr. Now here, this one is always the same, always, as long as you go through step 1 and step 2. Here the next step, it will be ddx of y times the integrating factor, and to be equal to qr, where qr is the right hand side of the differential equation in step 2. So after step 3, we shall go to step 4. Step 4 says put integrals on both sides and then integrate to obtain the solution of the given differential equation. So I'll put integrals on both sides. Now for this left hand side is easier because this cancels, the effect of this cancels, you remain with yr here, but this one you have to use the methods of integration to come up with the integral. So what should be keen at is this step 3, because it is very, very vital. So with that, let's go through some questions. So question 1 came from UNEB 2019, paper 1, question 16b, and says solve the differential equation this, given that y is equal to 1 when x is equal to pi over 2. So this is the differential equation. Now here the coefficient of dy dx is positive 1, meaning that the coefficient of y, because this is y, the coefficient of y will now be our value of p. Therefore p is equal to cot x. And now that I've got p, I'll say that integrating factor r is equal to exponential of the integral of p, which is cot x dx. So that is how you can get this, what to integrate. You have to make sure that this coefficient is positive 1. Now when I integrate cot, I'll come up with ln x. But this one, this ln and this exponential, the effect cancels, so you remain with only sine x, which is here. Therefore our integrating factor r is equal to sine x. Now that is step 1, getting the integrating factor. What about step 2? Step 2 says multiply this integrating factor throughout this given differential equation. So when I do that, this is what I'm going to come up with. So here I put sine x to come up with this part. Here I put sine x to come up with this part. Here I put sine x to come up with this part. Then from step 2, you have to remember to quote step 3. What does step 3 say? Step 3 says d dx of y times the integrating factor will be equal to the right hand side of this differential equation at step 2, so which is to r. That is step 3. Then step 4, put integrals on both sides. Then for this side, like I said, this one is easier because the effect cancels out, so you remain with y sine x. But for this one, you have to use the methods of integration to come up with its output. Now when you look at this, the method to use will be integration by parts. So you come here and tabulate our values. One will be the column for sign, we shall start with plus minus plus. I think you remember that method of integration by parts. So next is the column for differentiation. For differentiation, I'll put here x, then differentiate x to come up with 1, differentiate 1, you'll come up with 0. When you get 0, you stop there. Then next is the column of integration. Integration, you shall put sine x. Integrate sine x, you'll come up with negative cos x. Integrate negative cos x, you'll come up with negative sine x. Then from there, we shall go back and say that now y sine x, which is the integral, or which is the integral of d dx y sine x, is equal to, now how was this part got? So this part is got by using this from here. So you move from here to here, then to here, so that it becomes negative x cos x, which is here. Then this is minus 1 times negative sine x, which is this part, then plus the constant of integration. Then we can simplify, and that will be our differential equation. But this is the general solution. They also want the particular solution because they gave you the initial conditions that y is equal to 1 when x is equal to pi over 2. Therefore, come and substitute for y and x and simplify to get the value of c. After getting the value of c, I'll come and substitute here to get the particular solution. So now we shall go to question 2, which came from UNEB 2010 paper 1 question 8, and says solve the differential equation this. So the first thing to do is to make the coefficient of dy dx equal to positive 1. Therefore, come and look at this. Here there is x, meaning that I will divide throughout by x to come up with this step. Then next I will look for the coefficient of y. The coefficient of y here is 1 over x. What does that mean? It means that p is equal to 1 over x. Therefore, the integrating factor will be got by integrating exponential of the integral. The integrating factor will be equal to the exponential of the integral of p dx. And p is 1 over x, so I'll come and put it here. When I integrate 1 over x, I'll come up with ln x. Now this ln and this exponential cancels, remaining with only x, which is here. Therefore, x is our integrating factor. After that, I'll come and multiply x throughout the differential equation at this point, to come up with this. Now this is why I told you how you can distinguish between exact and inexact. Now if you look at this differential equation is exactly the same as this which was given. Therefore, that means that the given differential equation was an exact differential equation. But because it is not easy to identify it, you have to go through these steps. After all, you'll be able to come up with the same differential equation. After that, we shall go the next step. d dx of y times the integrating factor equal to what is on the left hand side, which is that. Then from there, put integrals on both sides. So this effect cancels, you remain with xy, but here integrating ex, you'll come up with ex plus c. Now here they didn't give us the initial conditions, meaning that they only wanted this general solution. So now we shall go to question 3, which came from UNEB 2008 paper 1 question 16a, and it says solve the differential equation this. So still the same procedure will apply. First, make the coefficient of dy dx equal to positive 1. So divide throughout by x to come up with that. Then the coefficient of y is negative. I think realize that there is a negative here. So it is negative 1 over x. Therefore, p is equal to negative 1 over x, implying that the integrating factor will be equal to the exponential of the integral of negative 1 over x with respect to x. So integrating this gives me negative ln x. Now this negative can go up here to become ln x power negative 1. Then from there, remember that this cancels, exponential and the ln cancels. You remember with x to power negative 1. But x power negative 1 is the same as 1 over x. Therefore, that is step 1. Step 2 is to multiply this integrating factor throughout this differential equation. So I'll come and multiply throughout to come up with that. Simplify a little and be able to come up with that, because when I simplify this, you will realize that x and this 1x cancels, you remain with x ex squared, which is that. Then for this side, it is always constant. It will always be, as if here there is y, it will always be y multiplied by the integrating factor. But if here there is another value, another variable, it is what you put here. For example, if they say d theta dt, it implies that here you will put theta times the integrating factor. So what to put here depends on what is here. Then what to put here depends on what you have got as your integrating factor. Then next is to put integrals on both sides. So when I put integrals on both sides, this will cancel and I have to integrate this. Now if you look at this one very keen, you realize that the method to use is the method of recognizing presence of a function and its derivative, because differentiating this gives you 2x and this x is here. Therefore, when I use that, I'll come up with this cancels, remain with y over x, and here it will now become a half ex squared plus c, which is the constant of integration. Now they didn't give us the initial conditions, implying that that is what they wanted. So now shall go to question 4, which came from UNEB 2007 paper 1 question 16b, and says solve this given that y is equal to 2 when x is equal to 0. So here the good thing, the coefficient of y dx is already a positive 1. So what I will do, I'll just look for the coefficient of y, which is 2 tan x, and that will be the value of p. After getting p, I can easily get my integrating factor. It will be exponential of the integral of 2 tan x. Now when I integrate tan x, I'll come up with negative ln cos x, and this 2 is maintained, which is here. Then from there, the whole of this negative 2 will go up to become that. Then from there, realize that this cancels, remain with cos x raised to the power negative 2, which is the same as 1 over cos squared x. Now this is our integrating factor, and that is step 1. Now step 2 said you multiply this integrating factor throughout this differential equation. So when you do that, we are going to come up with this. Then from there, you will come and state this step 3, that y, because here it is y, so y multiplied by the integrating factor, and remember to put this ddx there because it is very vital, will be equal to qr. Now qr, you realize that this one and this one cancels and you remain with 1, so that is why we are putting 1 here. The next is to put integrals on both sides. So when I put integrals on both sides, this will cancel and will remain with y over cos squared x, but integrating 1 gives you x plus the constant of integration. Now here the good thing, we are given some initial conditions that y is equal to 2 when x is equal to 0. So when I substitute for y and x, I'll be able to get the value of c. And when I substitute this value of c here, I'll be able to get the particular solution. So now I shall go to question 5, which came from UNEB 2006 paper 1 question 7, and says solve the differential equation this given that when x is equal to 0, y is equal to 1. So here already the good thing is that the coefficient of y dx is already positive 1, implying that p is equal to 3. Therefore, the integrating factor will be equal will be equal to the exponential of the integral of 3 with respect to x. And then integrate 3, I'll come up with 3x, which is here. Therefore, I'll go to step 2, where I have to multiply this one throughout this differential equation to come up with this. Then I'll go to step 3, where I have to state that d dx of y times the integrating factor is equal to r. So this multiplying these two gives you this, because same base you add the power, so 2x plus 3x gives you 5x. That is why you see 5x there. The next is to put integrals on both sides. Then this will cancel, it is easier. Then here it's an exponential, I can also easily integrate it. So when I integrate this, I'll come up with 1 over 5 exponential of 5x plus the constant of integration. But y is equal to 1 when x is equal to 0, because it was given here. Therefore, I come and substitute for x and y to be able to get the value of c. And c will be equal to 4 over 5. Therefore, substitute this c here to come up with a particular solution. So now we shall go to question 6, which came from UNEB 2004, paper 1, question 16a, and says, solve the differential equation this. So here the coefficient of dy dx is tan x, meaning that you have to make it positive 1 by dividing throughout by tan x. When I do that, I'll come up with this. Then next is to identify that now p will be equal to 1 over negative 1 over tan x, but remember 1 over tan is equal to cot. That is why here you see cot, and here also 1 over tan is cot, so it will be sine squared x plus, multiplied by cot x. That is why you see it there. Now from there, the coefficient of y is negative cot x. That is what we shall use to get the integrating factor. So integrating cot x gives you ln sine x, but remember there's a negative here, so you bring it there. Then after that, you'll have to take this negative up here to come up with this. Then this cancels, you remain with that. After that, you remember that this one from the rules of indices, this is the same as 1 over sine x. So that is our integrating factor, and that is step 1. What about step 2? Step 2 says you are going to multiply that integrating factor throughout this differential equation. So when I multiply throughout, I'll come up with that. Then go to step 3, where I have to quote that d dx of y times the integrating factor is equal to what is on the left hand side, and that this left hand side is the same as r. So I'll try to simplify. This is y over sine x, which is here, and this one cot x is the cos over sine. Now at this step, you realize that this and this is sine squared, and also this is sine squared, meaning that they will cancel. Therefore, on this side I remain with only cos x. Therefore, I come and write that d dx of y over sine x is equal to cos x. Then from there, I can now go to step 4, where I have to put integrals on both sides. Then this effect cancels and to gives you y over sine x. For this side, I have to integrate cos x to come up with sine x plus the constant of integration. Therefore, when I make y the subject, y will be equal to that. So that was question 6. Now we shall go to question 7, which came from UNEB of March 1998, paper 1, question 15b, and says solve this differential equation. So the good thing is that the coefficient of dy dx is positive 1. Therefore, I'll just look at the coefficient of y, which will be negative tan x, and that will be the value of p. Therefore, the integrating factor will be integrating this tan x gives you negative ln cos x. But remember, there is also a negative here, so negative and negative gives you a positive. That is why you say positive here. So you only have exponential of ln cos x. Now this cancels, you remain with cos x, which is there, and that will be the integrating factor. That is step 1. Step 2 says multiply that integrating factor throughout this differential equation to come up with this line. Then step 3 says you are going to set that ddx of y multiplied by the integrating factor is equal to what is on the right hand side, and that is this. But I already know that cos squared x is the same as 1 minus sin squared x. Therefore, in the end, when I open this bracket, I'll come up with x. This x cos x by 1 gives you cos x, and this by this gives you sin squared x cos x. Then I'll put integrals on both sides. Now, when I integrating means that this effect cancels, I remain with y cos x. But here, integrating cos x gives you positive sin x. And integrating this, you remember the method of recognizing presence of a function and its derivative. So the function is sin squared x, so you increase this power by 1 to come up with sin cubed x, then divide by the new power, which is 3 here. That is why you see 1 over 3 there, plus the constant of integration. So now we shall go to question 8, which came from UNEB 1996, paper 1, question 15a, and says find the general solution of the equation this. So the coefficient of dy dx is x, meaning that we have to make it positive 1 by dividing throughout by x to come up with that. Therefore, p is equal to negative 2 over x. Therefore, I can get the integrating factor, and integrating factor will be 1 over x squared. Then from there, I go to step 2. I have to multiply this throughout this equation to come up with this line. Simplifying further gives you that. Therefore, now I'll go to step 3, where I'll say that ddx of y times the integrating factor is equal to that. Then put integrals on both sides. This one cancels, but this one is a little tricky. So what you're going to do, let's first call it equation 1 and look at how we can integrate this. Now integrating, we are coming to that, but ddx of ex over x squared is equal to, now this is the quotient, so quotient means keep this one constant, differentiate this to come up with this, minus keep this one constant and differentiate this to come up with this, over this squared which is here, that is quotient formula. Now when I simplify, I'll come up with this. What does that mean? It means that therefore, if when I differentiate this, I'll come up with this. It implies that when I integrate this, I'll come up with that. That is why you can come here and conclude that this integral is equal to this plus c. Therefore, I'll go back to equation 1 and substitute that for that integral to come up with that. Then multiplying throughout by x squared gives you that. So now we shall go to question 9, which came from UNEB 1994, paper 2, question 9a, and says solve the differential equation this, given that t is equal to 3 when theta is equal to pi over 2. So the good thing is that the coefficient is already a positive 1, implying that this coefficient, I think you see that here it is t, implying that the p will be equal to the coefficient of t, which is called theta. Therefore, r, the integrating factor, will be equal to exponential of the integral of cot theta d theta, and this integral is equal to ln sin theta. Therefore, this cancels, you remain with sin theta. Then next we shall go to step 2. We have to multiply this one throughout this differential equation to come up with this line. Then next is step 3, where I would say that d theta is equal to t times the integrating factor is equal to what is on this right hand side, which is that. The next is to put integrals on both sides. So this one, the effect can cancel, but for this one, this is half angle, so this one is the same as sine 2 theta from the trigonometrical identities. So integrating it gives you negative a half cos 2 theta plus c, which is the constant of integration. But you're given these initial conditions, so I'll substitute for t and theta. Remember, calculator should be in radians. So I'll be able to get the value of c as 5/2. And substituting this one here, I'll be able to get the particular solution. So now shall go to question 10, which came from UNEB 1991, paper 2, question 9a, and says, solve the equation this, given that y is equal to 2 when x is equal to 0. So here the equation is x squared, meaning I have to first make it positive 1 by dividing throughout by x squared to come up with that. Then p is equal to this coefficient, which is 1 over x squared, which is that. Therefore, the integrating factor can now be got, and it will be equal to e of negative 1 over x. Therefore, multiply this integrating factor throughout this differential equation to come up with this line. Then from there, go to step 3, where it will be ddx of y times the integrating factor is equal to what is on the right hand side. So this one, you realize that it is same base, so you add the powers. This plus this gives you 0, so it powers is 0 is equal to 1. Put integrals on both sides, will come up with that. So this cancels, you remain with this, and here integrating 1 gives you x plus the constant of integration. Now the good thing, we are given the initial conditions, meaning they want a particular solution. So this is called the general solution, but when you are given initial conditions, you have to get the particular solution. So shall come and first substitute for the value of x and y. So when I substitute, I'll come here and say that y is equal to 2 when x is equal to 0. Therefore, substituting gives you that. And in the end, the value of c will be equal to 2, and substituting that 2 in the general solution gives you the particular solution. So now we shall go to question 11, which came from UNEB 1990, paper 2, question 3a. It says, find the general solution of the equation this. So the good thing, the equation of dy dx is already positive 1, therefore p will be equal to cot x, and integrating factor will be equal to e of the integral of cot x. So this integrating cot gives you ln sine, and this one cancels, you remain with only sine x. Step 2, you multiply throughout this differential equation to come up with this line. Then step 3, you quote that ddx of y times the integrating factor is equal to what is on the right hand side here, which is that. Then step 4, put integrals on both sides. So put integrals on both sides. Here it is easier because the effect cancels, you remain with y sine x, but here you have to integrate. Now here you realize that it is a function and its derivative, therefore you'll be able to come up with, and the function is sine x squared, therefore integrating will give you sine, increase the power by 1 to become sine cubed x over the new, divided by the new power, which is 3. But remember, there is also another 3 here, so 3 over 3 gives you 1. That is why there is 1 here, plus the constant of integration. So that brings us to the end of this video. Thank you for watching, and be reminded that the next video will be on application of differential equations. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video on applications of differential equations has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.